Hello, hi everybody. Welcome to this sixth video of the chapter of vectors named as mathematical methods. In the previous video, that was part number 5, we have studied about parallelogram law of vector addition. By using several simulations, we have seen how exactly the geometrical interpretation of that law is. And we have said there at the end that in the next video we are going to speak about the mathematical proof for finding the magnitude as well as direction of the resultant vector. So basically, to find the addition of vectors or to find the resultant of vectors will be very simple for us. If at all the vectors are represented in the form of xi cap plus yj cap plus zk cap, you just have to add their x components together, y components together, z components together. But when the vectors are represented with their magnitudes and angles between them, and if I have to find what is the resultant in magnitude and direction, then this mathematical proof of parallelogram law of vector addition is going to help us a lot. I will once again start with the revision of the statement of parallelogram law of vector addition. The law states that if at all you have two vectors of the same type represented in magnitude and direction, they are by two adjacent sides of a parallelogram, then the resultant is represented in magnitude and direction by the diagonal of the parallelogram starting from the same common point. Now let's go for the mathematical proof of this particular thing. I'll just move myself down a bit. Here in this mathematical proof, let us consider in the diagram I have got two vectors. One is vector OA here, which is represented as vector P. The other is vector OB, it is called as vector Q. So we have got two vectors, vector OA as vector P, vector OB as vector Q, such that they will have certain magnitudes, and those magnitudes are taken as only P and Q, capital P, capital Q, such that mod of vector A is equal to P and modulus of vector OB is equal to Q. They are both acting at point O here, such that angle between them is equal to theta. As you can see in this particular case, theta is the angle between these two, vector P and vector Q. In order to find this resultant or addition of these two, I have to complete my parallelogram O, A, C, B. I complete this parallelogram and OC gives me the resultant, vector R. So that is what the law says. According to this particular law, you have vector OC is equal to vector R, such that magnitude of OC, which is equal to only R, I would represent, it is the magnitude of the resultant vector. What I now want to do is, I have to find out what is this value of R equal to in terms of, now the things which are known to me, they are value of P, value of Q and value of theta. So these three things are known to us and I have to find out what is the magnitude of R. In order to do that, what I just have done here is I have made a simple little more adjustment geometrical construction. I have drawn this CD perpendicular to the extended part of vector OA and such that CD is perpendicular to OD is my consideration. Now in order to find out this magnitude of R, I will just first of all take into consideration this bigger triangle ODC. In this triangle ODC, I try to use Pythagoras theorem, and according to Pythagoras theorem, I would find that OC squared is equal to OD squared plus CD squared. Out of this, OD itself is addition of OA and AD. So here I have said, but OD itself is equal to OA plus AD. Then I would substitute that there, and then my equation becomes that therefore OC squared is equal to OA plus AD the whole bracket squared plus CD squared, which if I go for its mathematical simplification, it will tell me that therefore OC squared is equal to OA squared plus 2OA into AD plus AD squared plus CD squared. Out of which these last two terms, that AD squared plus CD squared, if I go for, this in the smaller right angle triangle I find AD squared plus CD squared, that will be equal to AC squared. But that AC itself is equal to Q, as I know. It's equal to Q in magnitude. So this AD squared plus CD squared, in the next step I would write it as AC squared. And then my equation remains as it is, except the last two terms I am going to write AC squared. So therefore OC squared is equal to OA squared plus 2 AD plus AC squared. Then I start substituting what their values are. OC is equal to R, which I actually have to find out. So therefore R squared is equal to, now what is OA equal to? OA is equal to P. Then that OA is equal to P. So this will be P squared plus 2P into Q cos theta. Instead of AD, I am writing it as Q cos theta. How am I writing that AD as Q cos theta? I have written its mathematical reasoning in red here. That in that smaller right angle triangle, I find cos theta is equal to AD divided by AC, which is equal to Q. So it is AD divided by Q, and therefore AD is equal to Q cos theta I have. And I can substitute that, and after substituting that, this entire equation will start looking to me like R squared is equal to P squared plus Q squared plus 2PQ cos of theta, and therefore the magnitude of the resultant R, which I have to find out, I can write that therefore R is equal to root of P squared plus Q squared plus 2PQ cos of theta is what I would go for. And this is exactly what I wanted to find out, the magnitude of resultant. And on the right hand side, I find all the three things P, Q and theta, they are known to us, and you can then find what is the magnitude of R. So this equation gives me what is the magnitude of vector R. I would then go for finding out what is the direction of vector R, but before that I will go for its special cases. Special cases means the cases which are actually known to us even before knowing this particular formula, that supposing if the two vectors P and Q, they are in the same direction, then you simply have to add them up. So it tells you that if theta is equal to 0, then vector P and vector Q, they are in the same direction. Cos of theta is equal to 1 I have, and therefore this equation number 1 of mine, in this if I put cos theta is equal to 1, it would give me that therefore R is equal to root of P squared plus Q squared plus 2PQ, which in fact is equal to P plus Q the whole bracket squared. So since that is equal to P plus Q the whole bracket squared, I observe it is only equal to P plus Q. So this is what was known to me, that when I have this R is, P and Q both are in the same direction, the resultant R is only equal to P plus Q. In this, one more special case I can add, that if at all P and Q were of equal magnitudes and in the same direction, means P and Q both were equal and they were in the same direction, it was just twice of P or twice of Q. We have actually seen simulations for this, that supposing if I have vector this is, let me say 8, this is 8, and both are in the same direction, I would take it to be. So if these two are the vectors, then their addition, if you go for any kind of law, you would find that that is actually equal to twice of them. So here vector D plus vector E, their magnitude is actually equal to their additions. So I can just see that F is the addition of D and E here, so it is equal to the addition of their magnitudes. That is what this special case is telling you. Now I go for the second special case. If at all my vectors were 180 degree opposite, that is exactly opposite in direction, then cos of 180 degree is equal to -1, and the R value will be in your equation 1. If I substitute that R is equal to, you will get it as root of P squared plus Q squared minus 2PQ, which will turn out to either P minus Q or Q minus P, whichever is greater, minus the smaller vector. So that becomes your resultant R. Whether this is true, of course we know that this is true. You can actually check it here. that instead of this, I will take that angle theta to be equal to 180 degree opposite, and by taking that angle of 180 degree opposite, now I would find that let us say vector D is taken little of greater magnitude, E ला थोड़ा सा लहान करतो, that D is of magnitude equal to 10, here I have, D चा magnitude 10 है, E चा magnitude it is equal to 4, so it is here, the resultant would be 10 plus of minus 4, so that's equal to 4 only. So this has to be equal to the difference between those two. Actually addition is equal to the difference of those two. That's what this second special case, and you can actually see that it is equal to the difference here. So it matches exactly. So that was about this thing. The third special case was if at all P and Q were perpendicular to each other. Achha, if at all P and Q in this itself were equal, the value of R would be equal to 0. Even that can actually be seen by using this particular thing, that if I take D is in magnitude equal to 10 and E is also in magnitude equal to 10, then vector F is not absolutely seen to be anywhere, because vector F has got 0 value now, and that's why it is not seen. The moment I change this a bit, E ला जर का मी 9 केलं, if I make E as 9, I still have that F is equal to 1 as a difference, but the moment both are equal and opposite, their addition will be equal to 0 vector. That is what you say, that whenever the two forces are exactly opposite to each other, acting at the same point and along the same line of action, you would have the resultant vector to be equal to 0. The vectors would cancel each other's effect. So that is what is seen in this particular case. If at all, if theta is equal to 90 degree, that is the two vectors were perpendicular to each other, then you have R is equal to root of P squared plus Q squared, because your cos theta value is equal to 0 mathematically. Here if I put cos theta is equal to 0, you will find it's only root of P squared plus Q squared. The third term entirely will just vanish out. So this will be R is equal to root of P squared plus Q squared. This thing also can be verified by using simulations, that if at all D and E are you can say equal in magnitude, I would take them equal in magnitude but 90 degree to each other. So that vector D is here and vector E is here. Both are 10 and 10 in magnitude. I would just see that they are either like this or here, wherever you consider them to be, and this is supposed to be your addition. This magnitude has to be equal to I can say 10 root 2. 10 root 2 will approximately turn out to 14.14 something. 14.14. So this diagram is showing 14.1. So it is very much alright. So that is how you can understand that whenever P and Q are perpendicular, R is equal to root of P squared plus Q squared, as you can see here. In this, once again, if at all P and Q are equal, then R is either equal to root 2 times of each of the vector, either root 2 times of P or root 2 times of Q also you can consider. The further two more special cases are not really the special cases, but I have added them as the special cases because in most of the multiple choice kind of questions, these things are frequently coming. Theta is equal to 60 degree and 120 degree, and we have to use them so very frequently. And that too in those when the two vectors acting simultaneously at the same point, they are of equal magnitude, like P is equal to Q and theta is equal to 60 degree. This equation would be R is equal to root of P squared plus Q squared plus once again P squared, or 3P squared or 3Q squared. So it will be root 3 times of P or root 3 times of Q. Now this also can be seen mathematically, that if at all I put P is equal to Q and theta is equal to 60 degree, this is 10, this is 10, the resultant has to be root 3 times of 10, that is 1.732 multiplied by 10, that would give me 17.32. So here they have said 17.3, so that's correct. Whereas if at all you have theta is equal to 120 degree and they are both equal in magnitude, in such case you have addition is actually equal to the same each vector. That if at all I take in this particular case, theta is equal to 120 degree, in this case I would then find that resultant is also equal to 10. you can actually take their you see vectors and try to see that vector law of parallelogram is also matching. So that is what I wanted to show in this particular thing.